talk a little bit more about this part of the handout. My goals here are to try to make connections with previous classwork that you've had. I also want to introduce the idea of statistical significance of parameters in a structural equation model. The other reason to explore all kinds of structural models with 3 variables in it is these models represent tricks that we use in structural equation modeling to make models that correspond to what we want to conjecture about reality. Let me tell you a little story. I mean, way back when the Earth's outer crust was cooling, and I started here in 1989, I was the first quantitative psychologist that they hired. And part of my job was to do consulting hours. And, you know, being an assistant professor, I sat in my little room with the door open, hoping somebody would come in and talk to me because I don't know anybody. And students and faculty would come in and I'd have a really funny discussion. They would say, okay, I did this analysis and I need the write-up. And it might be, say, a regression. And I'd say, well, here's the APA style manual. We can walk through and talk about what you're doing. They say, no, you don't understand. I need the write-up. And to make the long story shorter, what they were asking was they wanted an example of a published version of the model that they were doing. So if, for example, they had a 2-predictor regression, they wanted me to tell them about an example of an article where a person did a 2-predictor regression, and if they had if that article had a scatter plot, they would put in a scatter plot. And if they had a table of regression weights, they would put in a table of regression weights. And it took a little while to convince people that that really wasn't a great model, because often the things that you choose to present are different depending on what you really want to say or what your data are showing. In the same fashion, these 3 variable models are examples of ways that we adjust for the effects of another variable, or try to test for unique effects, or invoke a functional relationship between a predictor variable and a criterion that might have a form like quadratic regression, or answer questions about what groups are different than what other groups. And in this chapter, we're doing this all with squares, with manifest observed variables, but we can just as easily swap out circles for any of the squares that you see. So structural equation modeling is a somewhat poorly understood issue. And often when you're dealing with editors or colleagues or advisors, they'll say, well, that's your picture that you have, but I've never seen it published before. And the answer is not to go out and find the write-up, but to explain to the person in real world terms what the model is saying or what hypotheses it's testing. Second objective is I want to talk about statistical significance and what it is when we are testing the statistical significance of a parameter versus comparing a more general model to a more restricted model using something called the likelihood ratio test. And third, I thought, well, to try to make something useful for you, rather than give you homework assignments where you have an exercise to solve, I tried to think of a question that would be something that you might be expected to do in proposing your master's thesis. Namely, maybe I'd be interested in looking at the statistical power of a particular 3-variable model. And I also might be interested in comparing a model that is generated based on one model and exploring some other model. So that's, my goals here. And I realize that that sounds like a very tall order for a lot of, just one chapter. But those are the instructional supports and challenges that I want to look at. So just to rehearse, this is what the structural model looks like for a 2-predictor regression. And we talked about this a little bit last time, but if we're looking at correlations and standardized, this is what my correlation matrix might look like. That means that the variance of the predictor variables will be the number 1. The sling is going to be the correlation coefficient, and these will be my standardized coefficients. And we talked about the tracing rules here, that this model is saying that the correlation between my predictors is this single number. And the correlation between this predictor and that criterion is the number 1 times this weight plus this correlation multiplied by the other one. And the same song, second verse, applies to the other one. And then finally, the variance of the criterion variable is equal to all of the paths that start at the criterion and end up at the criterion again. So the variance of this criterion variable, if I'm looking at analyzing a correlation matrix or z-scores, is going to be E plus, there's another way to go, backwards on A times 1 times A plus A times the correlation times the other regression weight B plus B times the number 1 times B plus, we get to run around the bases the other way, B times C times A. And all of those numbers will add up to 1. The R square for the model is all of the tracing rule paths that are kind of from the neck up that involve the predictors. 1 minus the R square is the standardized variance here. That's also known as the coefficient of non-determination, if you happen to have had a regression book that talks about that. R square is also sometimes called the coefficient of determination. This is just vocabulary. Now, secondly, to rehearse this, if I'm looking at analyzing a variance covariance matrix, if I'm interested in assessing the proportion of variance in the criterion accounted for by the predictor, it's the same thing. It's just that now I'm going to be putting on the variances and the covariances. So this will be the variance of the predictor, the variance of the predictor, the covariance, and the covariance of this predictor and the criterion is going to be this times this, and same song for the other one. And the variance of Y is going to be A times the variance times A plus B times the variance times B plus, I'm being tricky here, 2 times A times C times B. That's because I get to run around this model twice. I can just count that as 2 plus the variance. This thing down here, if I'm analyzing a variance covariance matrix, is the variance of error. It's the variance that you would find if you calculated the observed Y, the preserved criterion, minus the predicted Y for all of your data, squared them, added them up, and divided by n. Okay. Now, for some of you, this is old hat, and I appreciate your patience. For others of you, it's the first time I've seen this. So are there questions about this?
I have a question related to metrics. So if can you a little bit go up, like scroll up
Okay.
to show the metrics.
Okay.
For here, yes. So for here, for example, if you look at don't mind on the at first, and then let's say last 30 days. So when we make correlation, it says BVD plus ACTD.
Mm-hmm.
So for this one, for example, so do we start from last 30 days and go to don't mind, or can we do just the opposite, start from don't mind and go to last 30 days? So is this, does it matter where we start and where we go? Or can we start from last 30 days or from other variable.
That is true. In other words, this variance covariance matrix is symmetric. That is, you see the same number here as you here. And if you want to think about it, you can, just as you say, go backwards, start here, and say, what does this diagram say about the covariance of cigarette use with smokers? I can go backward and collect the error. I can go backward and collect this covariance and end up here. So you can do that. It's just a little bit easier for people who are starting out to think about it as going from your predictor to the criterion. And maybe that's a little natural for people because you tend to think of this as an explanation of cigarette use. The other thing I want to make a mention of is, a path diagram that looks like this talks about an equation. This is y is equal to A times smokers plus B times don't mind. So that's another way of understanding structural models, is to put it into an equation. All right. Okay, so let's talk a little bit about regression. Sometimes, certainly not us here, you'll find when you're doing a regression and you have lots and lots of predictors that the researcher will do a regression and they'll look at all of these regression weights and they'll say, well, which ones of these are statistically significant? And if they're not statistically significant, they say, well, obviously this means that that predictor can be removed from the model. But why might that not be a good idea? Let me put the question another way. What does this regression weight tell me about the relationship between the predictor variable and the criterion?
The amount of variance explained by that predictor.
Okay, that's part of it. But what special about that amount of variance is there? So if, for example, I'm predicting, I'm doing a study right now, predicting undergraduate GPA, and I've got ACTs and I've got high school core GPAs. If I find that ACT doesn't predict grades, I'm looking for a refinement of the amount of variance, period. So if, for example, I did a study with just this predictor in, would I also find that that regression rate isn't significant? That's a good question. That's a good way to do it. That's a good way to lead it. Right? So if I run this model and I find this in the two predictor model, it's not significant, will I necessarily find, if I just throw this predictor out, will I find that this regression weight is also not going to be significant?
I guess it could be that there's redundancy in the model. Is that?
Yes. Yes. So this regression weight is answering the question, is there redundancy? That is, these two bits of information may be overlapping. And by redundancy, Joy, means they're overlapping bits of information. And this regression weight answers the question, is there something unique about this predictor that contributes to the criterion? So just because it's not statistically significant doesn't mean that you can go through and just drop the item. It may well be, it answers the question, is there something unique about this? Maybe in this case, these two manifest variables are indicators of a general factor, a common latent variable of attitudes towards smoking. Or in the case of high school grades and ACT, those things are so highly correlated that I'm not getting anything unique from ACT, but maybe high school grades do give me a little bit of unique information.
So if you suspected redundancy, what would be your path forward? Like, how would you proceed?
Well, here's the magical special sauce of structural equation modeling. We would then, if our predictors are highly correlated, we're going to make a circle here and say there's a latent variable and point that latent variable at my criterion. Actually, that, in terms of a picture, where are we at? And that looks like, well, ignore the triangle for the moment. That is what this thing is. Apart from arranging these two things differently, I'm saying I'm going to have my latent variable point at my criterion, and the correlation between these two variables, as well as the regression we're predicting the criterion, are explained by this latent variable. So that's kind of the nice things about it. So if you're looking at psychopathology, if you're looking at public policy, you know, there are common economic characteristics. This is a little bit why structural equation modeling figures so prominently in policy and economics. A lot of things are correlated. And the reason they are correlated is due to one common process.
I have a question. So for SAT example, for example, but we need to be sure, or do we need to be sure that SAT on its own, when we look at separately, need to predict our variable? Is that correct? Otherwise, I think there is no meaning to put the model. So I mean, so the thing is, I think you emphasize that sometimes we put a variable into the model, even if it is not significant, just to look at the effect, like the unique effect of the other variable. So. So my question is, but to do this, we need to be sure that these variables, like the variables that we put into model, when we look at them separately, not before putting them into the model together, when we look at them separately, they need to predict outcome. Is that correct? Otherwise, I guess there is no meaning to put into the model.
Yeah, so let's talk about our skill sets here. So from regression, when we have many, many predictors, the strategy is to actually conduct all of the possible regressions, all of the one predictor models, all of the two predictor models, and so forth. And reporting out from a regression analysis amounts to saying, I examined all of the models, and here are the following, say, two predictor models, which appear to have approximately the same R-squares. And, you know, those are just viable candidates on the ground for you to consider. And inside of regression, we have other follow-up tests that we do, because those R-squares, those individual models, are themselves liable to criticism. Maybe one model has an R-square that's similar to others just because I happen to have one really weird person who was influential in the observations. And we'll talk about that when we get to influence diagnostics later. But I mean, you end up having to say, here's the universe and these are the viable models. And there really isn't a way out of that. The other thing that I wanted to comment on about regressions is we really don't believe them, because notice in this model, the predictor variable has no error variance. We are assuming in the multiple regression model and the analysis of variance model that the independent variables fell from heaven. They are measured, whatever they are measuring, perfectly. And so it's a little bit ironic when you read a paper saying, here's my scale of, you know, how smokers are trying to be mature with the items, and here's the coefficient alpha. Oh, and here's my multiple regression. Because inherently, you are ignoring the fact that your regression model assumes that your predictor variable has no measurement error. Contrast that with the 3-indicator factor model, where I am now estimating an error term for all of the variables. And in that respect, conclusions about this model are not liable to the criticism that, well, actually this variable isn't that reliable. Whereas when I'm looking at a regression, excuse me, when I'm looking at a regression, you might say, well, this one is significant and this one is not, but the reason could be that maybe this is a less reliable item. So we don't really know in regression. Okay, so those are some of the little cobwebs or some of the little reminders from classes that you've had before thinking about regression. So we've talked a little bit about regression with an intercept. It looks like the same picture. Looks a little bit like a robot, but I've got the little triangle of ones, a column of ones that will tell me the means of the predictor variables. And it also gives me the regression intercept. And the thing I wanted you to remember is when I am pointing from the column of ones at any variable, the interpretation of the dependent variable now becomes the variance covariance matrix. And these are the tracing rules. It's the same thing. My predicted matrix here is now a statement about the adjoined sum of squares and cross products matrix. So whenever I'm looking at it, the column of ones is going to have an average sum of squares and cross products matrix of 1. And the mean is going to be, the predicted means will be on the off diagonal associated with the column of ones. In this case, it's going to be 1 times 3 is the mean of this variable, 1 times 4 is the mean of that variable. The mean of the criterion is 1 times 3 times 0.31 plus 1 times 4 times minus 2.8 plus 1 times 2.17. And the little reminder is these numbers here, this part of the matrix that looks symmetric. So did I put the numbers in? I thought I had the adjoint sums of squares and cross products. I know it's in here somewhere, but this matrix is now the average sums of squares of trying. It's not the variance. So the average sums of squares of this predictor variable is 4 times 1 times 4 plus this sling. And similarly, the average sums of squares of this variable is going to be 3 times 1 times 3 plus this number. And for your, for your study, this is what the covariances also look like. Notice that, that the variance, the average sums of squares associated with the criterion gets to be a big ugly thing. Don't worry about it. Computers do this for you, okay? Conceptually, what's important to know is this functions, you can kind of play the game outside of the column of ones and you'll get the variance components that Joy mentioned before. If you want to talk about the average sums of squares of that variable, that involves the variance components plus all of the trips that are involved using the column of ones. So that's been the first half hour. And it kind of brings us up to where we left off the last time.
Can I clarify something quickly?
Mm-hmm.
In that model, going back up just a little bit.
Yep.
So when we're looking at the sums of squares, when we're asking that question, we're always going to start from the 1.
Mm-hmm.
Or we're asking a question about a mean or the sum of squares, we're always starting at the 1.
When you're asking, yeah, you're starting at the 1 and going somewhere, right? Mm-hmm.
Okay.
Yep. And when you're talking about the average sums of squares, you're going to start at that variable and end up back at that variable. So for example, the average sums of squares of predictor, I'm going to start here, go back and plus this. Okay. So just to kind of remind ourselves that you can go forward, but you can't go back. If I were doing this covariance, I can't take the 1 and go forward and catch this sling and get over there, because that would be taking 2 slings. If I were also doing, what does this model say about the average sums of squares of smokers? I can't go backward here, go forward here, take the sling, go forward here, and take the sling again. Those are not allowed. And I wrote those out here for you. Right.
So is there a sling under 1 under intercept?
I'm sorry, what?
I said, is there a sling under intercept?
It's understood to be there, yeah. I mean, I should really put a little sling on it and put it 1, but the people who do the RAM diagram path modeling do not put a sling there. But that sling is, because the sling is always going to turn out to be the number 1. The column of 1s is kind of a special variable that way.
Okay, thank you.
So now a little bit of the language Joy mentioned before. We can talk about relationships between our 3 variables. If the sling between 2 variables, 2 predictor variables, is 0, those 2 variables are said to be orthogonal. And there are 2 other terms, suppressor effects and redundancy. So redundancy occurs fairly frequently in regression models, mainly because bad things tend to happen together, like the year 2020, or good things, supportive things like children who do have high vocabulary scores, tend to have books, tend to also be from higher SES backgrounds, tend to have better teachers, those types of things. Well, redundancy means that the paths going from a predictor to the criterion, all those paths have the same sign. So in this case, this regression model illustrates a pattern of redundancy, because traveling from this predictor to this criterion is a positive number times a negative number plus a negative number times a positive number. Similarly, for this predictor, this is a positive number times a positive number to go from this predictor to this predictor. And similarly, going the other path is a negative number times a negative number. So these 2 predictor variables are kind of the overlapping bits of information that we were talking about. So whenever we're talking about 2 or more predictors where all of the paths are the same sign, that's a redundancy situation. And statistical suppressors, well, it's kind of a funny thing. It's an unfortunate term for psychologists, because suppression tends to be thought of as a negative thing. But suppressor effects occur when one of the paths from a predictor to a criterion is positive and the other one is negative. So if, for example, this A value would have been positive 2.8, we would have had a case of statistical suppression, because this would have been a positive times a positive plus a negative times a positive. Now, under issues of suppression, it becomes possible to have a standardized regression coefficient that is larger than 1 or smaller than -1. And this is not a sin, this is not a problem. This is when we get to talking about vectors and what a vector diagram means. We can't think of our standardized coefficients as representing correlation coefficients, because they're arrows, not slings. And a value of larger than 1 or less than -1 is not problematic per se. What is an issue, folks, though, is that statistical power is different depending on whether you have orthogonality or whether you have suppression or redundancy. You have the most power when your predictors are uncorrelated, and you have less power when your predictors demonstrate suppression or redundancy. And this is because the standard errors and the correlation between the parameter estimates becomes larger, and this starts to affect power. This is leading into my discussion of statistical significance. So a little bit of advice for you if you're planning a study. There's nothing that says that you need to go out and gather a random sample of Psych 1 students, unless you're interested in generalizing to that population. If you are simply interested in understanding the predictors of a criterion, you could design your study so that your predictors are orthogonal by quota sampling. In other words, if I were interested in looking at smokers trying to be mature and don't mind if I'm around smokers, I might assess those two items in mass testing and then select an equal number of people on the other variable for each level of the predictor. And in doing so, because I would have, for every person who said the number, answered strongly agree on mature here, I would have an equal number of people at all levels of smoking. Don't mind if you're around smokers. In other words, they have someone who answered a 1, a 2, a 3, a 4, and a 5 to that question. By putting equal numbers of people in those, this correlation will be 0. And therefore, I will be able, with a smaller sample, to find statistically significant relationships here. And these coefficients will be the same as would have arrived at if I would have done a random sample. It's just that my standard errors, my statistical significance would be larger. So let's talk a little bit about statistical significance. When you do a regression, this is what the printout looks like if you're playing with SAS. You have a regression for the model. And downstairs, we have statistical significance associated for the intercept and our two predictor variables. Well, let's kind of rehearse a little bit about this. What does this statistical significance mean? Well, I have two predictors in my model. This F statistic answers the question, is the predicted variance in Y based on these two models appreciably different than 0? And you can ask that question in a proportion model as well. I can say, is this proportion of variance statistically different than 0? And down here, I've got a parameter estimate and a standard error and a t-value and a p-value. Well, kind of to rehearse this, what is this t-value? Well, this is the regression weight that I have divided by the guess about the standard deviation of this regression weight if I were to do my study over and over again. This number divided by 0.03 is minus 8.80. And if the null hypothesis is true, and the data actually come from a population where this regression slope is 0, I should observe a value this large or larger, less than 1 time in 10,000. This is called the sampling distribution. Now this t-distribution here looks a lot like the normal distribution that we all know and love. The only thing about the t-distribution is it's a nice symmetric curve, but it gets flatter and flatter. The tails get bigger and bigger the smaller the sample size you have. So when I have multiple predictors, I need to start thinking about not only the standard deviation here, but also how errors of prediction here start to affect errors of prediction here. I'm going to say this slowly. It's kind of helpful if you think about this in path diagram form. So here I've got my regression. And let's assume I'm looking at my minus 0.28 number based on my data. Well, if I guess a number that's wrong, say minus 0.3, that's going to cause me to guess a number over here that's going to be a little bit smaller than it ought to be. Because the correlation between smokers trying to be mature in the last 30 days is going to be this wrong number multiplied by this number times this number. I've got to kind of make up the difference in my guess of this parameter estimate by adjusting this number. What I'm trying to say is a mistake over here is related to a mistake over here. And that's going to be a larger mistake depending on how highly correlated your predictors are. If I had an orthogonal situation, I wouldn't have to worry because this would be a 0. And a guess over here that's wrong, an error of prediction of that slope is not going to affect this at all. Now, when you had regression with more than one predictor, this was what the formula looked like. Well, it kind of looks a little familiar. We talked about matrix algebra. X prime X, my deviation score matrix of predictors divided by n, that's the variance covariance matrix of my predictors. And I'm taking the inverse of that. And I'm multiplying that by the error variance in my model. And this little C matrix itself is a variance covariance matrix of errors of prediction of the regression weights now. So in this example, I have 2 predictors. So this C matrix is going to be a 2 by 2 matrix. What will sit on the diagonal of that 2 by 2 matrix is the variance of the standard error. That is, it's going to be this, this number squared. And what will sit in the off diagonal is the covariance between the estimate of one regression weight and the other regression weight. So, and I'm saying this slowly, and it's not something that you need to have at the tips of your fingers when you think about things. The large message is when my predictors are correlated, my parameter estimates become correlated. In issues of redundancy, my predictor variables might be correlated among themselves, but that means that C will have the opposite sign. That is, if I have redundancy, my regression weight estimate for error will, for one predictor, will be negatively correlated with my regression estimate for the other one. Okay. Now, there's a thing, right? This is the equation that you saw when you took regression. Notice the denominator, the sample size minus k, the number of predictors, minus 1. Well, structural equation model uses the same formula, but with a small difference. And that's down here. This is the variance covariance matrix for something called the wall test, for testing for the statistical significance of an individual parameter estimate. And it's the same thing as you saw before, but instead of n minus k minus 1, you see down here n minus 1. So C is going to be a little bit bigger, a little bit smaller than it ought to be if you were doing a regression model. And the reason that we divide by n minus 1 instead of n minus k minus 1 is in structural modeling, there's nothing that guarantees that I can even point at one variable and say this is a predictor. So I just divide by n minus 1 instead of n minus k minus 1. You can slap the hands of SEM programs like Procalus and tell them to divide by n minus k minus 1 if you want. That's somewhat useful if you're doing a regression with full information maximum likelihood. Generally speaking, it doesn't really matter unless you have a very small sample size. So if you have 900 people, the difference between 997 and 999 is slight. So you get essentially the same things out. Having said that, if you have a small sample size, there's a slight bias in SEM programs toward giving you statistical significance when you should not have it. And if you're looking at that for these data, this is what C looks like. The square root of this is going to give you the standard error that we saw in the regression analysis before. And over here is the covariance between this regression weight and that regression weight. Well, like I was saying before, this is a variance covariance matrix. I have no idea what the hell these numbers mean. I can tell you what the diagonal things mean, but should I be worried about this or not? Well, you can take this matrix and divide by the standard deviations, pre and post multiplying. This will give you a correlation between the estimates. This is telling you then that whatever you guess for one regression weight is going to be negatively correlated, the error will be negatively correlated with what you guess for the other regression weight. And as I mentioned before, when you have redundancy or suppression, the standard errors become larger. And when you have orthogonal studies, they're less than that. And now, the other thing that people do in research articles is to say, well, I ran a regression. This regression weight was significant, the other regression weight wasn't. So now I know that this is more predictive than that. And this is not true. So in my example of ACT scores and grades, since 1989, I've sat on countless policy discussions where people will say, ACT doesn't predict as well as grades. Well, what does a regression weight mean? It only tells you if that regression weight is different than 0. It does not test whether the standardized regression weights are different. And it doesn't test whether the unstandardized regression weights are different. That's a separate hypothesis. In our structural equation modeling language, if we want to test for the equality of regression weights, we come upstairs and we fix this number to be equal to that number. If we're using a regression program like LM or ProcReg, there's code in there that will tell you, please test the model that these two regression weights are the same. This is the code for ProcReg and SAMS. And I walk you through the equations for that, but since this is, this is here to reinforce some of what you had in regression before, the big message is if you are testing for the equality of unstandardized regression weights, you're just going to fit a model in which you constrain these paths to be the same and compare that with the fit of a model where those two coefficients are allowed to be different.